Alright, so this is the Pencast for Spring 2018 Physics 102 Midterm 1 Question 1. We are asked to consider an infinite line of charge with lambda line charge density and also a point charge plus Q. The first part of the question asks us to find the force on that point charge, which is due to the line. So if I have a line charge, this has actually cylindrical symmetry, so I can use Gauss's law to calculate the electric field a line charge creates at any point. For that, I will actually take a Gauss surface at a distance r from the line. Now, on that Gauss surface, Gauss law tells me that E dot dA is Q in divided by epsilon 0, and E dot dA from the top and the bottom, E by symmetry is radially outward. Top and bottom dA vectors are perpendicular to that, so it's only coming from the side surface, so it's going to be E magnitude, and on the side surface E and dA vectors are actually parallel. So if this Gauss cylinder has a radius r and height h, this is just going to be 2 pi r times h, which is the side area of the cylinder. How about Q in? What's the amount of charge inside? I have a section of length h with lambda charge per unit length, so this is going to be lambda times h divided by epsilon 0. H is cancelled, which tells me that the electric field magnitude is lambda over 2 pi epsilon 0 r, and it's radially outward. So we are asked to find the force on Q, and the force on Q will be just Q times the electric field at that point, right? So what's the electric field at that point? Well, I have Q, the magnitude of the electric field is 2 pi epsilon 0. R is the distance from the line to the charge, which is given as 2d. How about what radially outward means in this case? On the x-axis, it's just going to give me the direction of the x-axis, the I hat vector. So as a vector, Q lambda over 4 pi epsilon 0 d I hat will be my force vector. For part B, we have to calculate the electric field at a point which is given with coordinates d and d. Now there will be two electric fields. Let me try to redraw my figure. Right. I have plus Q charge here. Say this is D. This is D. Now I have two contributions. Remember the rule of superposition for electric fields. There will be an electric field created by the line charge, and there will be an electric field created by the point charge. And I'll find both vectors and just sum them up. Let's first find electric field of the charge Q. What's the distance between, so this is D, this distance, y distance is also D, which means the distance from the charge to the observation point is d square root of 2. So the electric field magnitude will be Q over 4 pi epsilon 0 2 d square, right? How about the vector now? This vector is, and this is making 45 degrees pi over 4 angle, so on the x-axis I have minus I hat over square root of 2, on the y-axis in the positive direction plus j hat over square root of 2. So that's the electric field of the point charge. Electric field of the line charge we calculated above, it will be only in the I hat direction, but this time the distance from the line to the observation point is d, so the magnitude is going to be lambda over 2 pi epsilon 0 d, and the direction will be I hat. I'm just going to add up these two vectors without forgetting that they are vectors. That's going to give me my result. So in the I hat direction, in the x direction, I have two contributions, lambda over 2 pi epsilon 0 d, that's a positive contribution, and then I have the negative contribution, q over 8 pi epsilon 0, and I'll actually do it as follows. This is 1 over square root of 2, so I'll actually write it 16 square root of 2 d square. You don't have to do this, but I like square roots in the numerator. And how about j hat? In the j hat direction, I have only electric field created by the point charge, which is again going to be 16 pi epsilon 0 d square, square root of 2. Let's check the units. Units seem fine because I have lambda over d here and q over d square, so I can add these up, and that is going to be my final result.